Alright, thanks for watching, and today I want to give you a beautiful glimpse into the world of complex analysis. And complex analysis, I cannot even describe how heavenly it is. Because all the stuff that was wrong in real analysis turns out to be true for complex analysis. So all the things you were worried about, like differentiating under an integral, maybe differentiating twice, or using power series, are totally legit in complex analysis. And let me give you a roadmap. I won't really prove anything, but just sort of the main topics of this course. So, of course, complex analysis, what is this? It's the study of complex numbers. So the first part would be to define complex numbers, which is just numbers of the form z equals to x plus iy, where x and y are real. Real, think, 2 plus 3i. And question is, what is this I? Well, it's an interesting story because, before I was invented, people are like, the square of a number has to be positive. But then I think there was Euler or something who came up with, this new definition and saying, hey, what if we don't assume that? Can we have more, new results? And in fact, it is true because I squared is defined to be the number whose square is -1. Technically a number because -1 also satisfies this. So it's really a solution to x squared plus 1 equals to 0. And I think it appeared somewhere also, I think in Cardan's formula or something, where they were like, well, I think they were studying a polynomial of third degree and they knew they were going to have 3 roots, but then they were like, wait, some of the roots are missing. It doesn't make sense. And that's also how I was discovered. Anyway, but that's not the point of today. The point is complex analysis. So you start by defining complex numbers, and you can do other cute things. For example, you can't just define complex numbers of x plus iy. You can also define this in the R2 plane in terms of polar coordinates. Saying, instead of saying x plus iy, you want to look at the radius first of all. So the distance between 0 and that number and the angle. And you can write this in a nice complex exponential form, which is just r e to the I theta. And r, that's called the r is called the modulus of your complex number, which is square root of x squared plus y squared. And theta is what's called the argument of the complex number. It's a very good argument for that. And it's the angle, and I think between 0 and 2 pi, it's defined to be the arctangent of y over x. But anyway, so once you have complex numbers, you can write them either in Cartesian form or in polar form, and you can do other cute things. You can take complex conjugates, you can take 1 over complex numbers, and other nice things. But as I said, this is called complex analysis, and analysis is of course the study of functions, and once you have complex numbers, you want to study complex functions, which is just functions from the complex numbers to themselves. For example, just consider the squaring function. You take a complex number and you square it. But remember, a complex number can be written in terms of real and imaginary parts, so x plus iy. So let's just take this function and write this in terms of real and imaginary parts. So x plus iy squared, that basically becomes x squared plus 2x iy plus iy squared. And I squared is -1, so you're left with x squared minus y squared plus I 2xy. So it turns out any complex function can be also written in terms of real and imaginary functions. Namely, you can write this as u plus iv, where in this case, u is x squared minus y squared, and v is 2xy. You might say, okay, but don't worry, I have a point. But let's cover a different topic for a second. So we have complex functions, and once you have complex numbers, you can also define limits. Once you have limits, you have continuous functions. And more interestingly, you can also differentiate complex functions, again, provided that they're differentiable. Namely, you just define f prime of z naught to just be the limit as z goes to z naught of the difference quotients. So f of z minus f of z naught over z minus z naught. And this is completely legit because the numerator is just a complex number. The denominator is a complex number. So you're just taking ratios of two complex numbers, which is a legit operation. And then limits, they're defined like real limits. So like epsilon and deltas if you want. And more importantly, if a function is called, if this limit exists, meaning it doesn't blow up and it goes to a certain number, then we call f to be differentiable. So differentiable at z naught. But turns out for complex functions, there's a cooler name. It's called holomorphic. It's like a hologram. Instead of saying differentiable, we say holomorphic or analytic, but I want to put off this term till the end because we don't know what analytic means yet. So f is holomorphic at the number if this exists. And now let's go back to this argument if you want. Any function can be written in terms of real and imaginary parts. And the question is there a convenient way to say differentiable, but with those real and imaginary parts? And in fact, there is. It's what's called the Cauchy-Riemann equations. So, which I've done a video on, by the way. So Cauchy-Riemann equations just says that if f is differentiable, I guess f is holomorphic, if and only if, and again I would like to remind you, f is u plus iv, if and only if u and v satisfy a nice system of differential equations, namely ux equals to vy and uy equals to minus vx. In other words, if the x derivative of u equals to the y derivative of v, and the y derivative of u is the minus x derivative of v, turns out the function is differentiable. Which gives us a nice way of just checking differentiability without even having to go to this limit. It's nice, and in fact, using those Cauchy-Riemann equations, we can prove other nice things. So, I think it's with those. But for one thing we can show is that suppose you have a domain D with a segment here. And basically, one fact you can actually show, suppose f is identically equal to 0 on that segment, then f must be the zero function. So very surprising result. In other words, a differentiable function is just determined by its value on a segment. So pretty impressive, and which is one of the surprising results of complex analysis. And I'll show you other surprising results. But before we finish that, and I forgot to say, that was part 2. Part 2 was about holomorphic functions. once you have those complex numbers, then you can fiddle around with those a bit more, and you can define something like e to the z or sine of z. For example, sine of z is defined as e to the iz minus e to the minus iz over 2I. And once you define e to the z, you'll have that. And more interestingly, you can define the log of z, which is a bit controversial, and I think I've either done it or will do it in another video. This function actually has multiple values because it turns out there are multiple angles or multiple numbers whose exponentials are equal to z. So this is a very controversial function. So just a heads up if you ever study that. Okay, wonderful. So what have we done so far? We defined complex numbers, we define complex functions and their differentiability, and now let's move on to the world of complex integrals. And unfortunately, you might think, oh cool, we'll integrate a function over the complex plane. Sadly, we'll not do this. I haven't seen this before, but I believe if you want to do this, you might have to use a Lebesgue integration or something, or abstract integration, but so far I haven't seen any useful results about this, so I'm assuming that's why people don't really study that. Yet, what you can study, and this is a more interesting thing, you can study an integral over a curve. So suppose you have a curve that's parametrized by gamma, and that starts at A, and that starts at B, ends at B, then you can actually define the line integral of a complex function over that curve. In a convenient way, just like in multivariable calculus, so it's the integral from the starting time to the ending time of f over that curve, so gamma t. And then dz is just dz over dt, which just becomes gamma prime of t dt. And so this is more fun. You can just integrate over circles, you can integrate over segments, any contour that you want. And this very innocuous definition actually has very surprising consequences. Because first of all, you may ask, suppose you have a closed curve. Let's say you have a curve C where gamma B equals to gamma A. So the ending point equals to the starting point. Question is the integral of f equal to 0? And there was also a question asked in multivariable calculus, and it's answered in the following theorem, which I like to call the following are equivalent theorem. And actually, when I took complex analysis, one of my colleagues, student friends, was writing this on the board. It was saying the following are equivalent, never gonna give you up, never gonna let you down, never gonna turn around and hold you, or however that song goes. But anyway, yeah, you've been rickrolled. Anyway, so it's called the following are equivalent theorem, at least in this video. Namely, there's an easy condition of checking if the integral of f equals to 0. So the following are equivalent. The integral of f equals to 0 for all closed curves C. If and only if, and this is similar to the fundamental theme of line integrals, if and only if f has an antiderivative. Antiderivative, capital F. And that just means, don't think fundamental theme of calculus, think derivatives. An antiderivative is any function whose derivative is f. And that's the same as saying, so if it has an antiderivative, it's actually easy to calculate the line integral over anything. because then, let's see, I guess the way you write this is integral from z1 to z2 of f of z dz. That just means a curve that starts at the point z1 and ends at the point z2. It turns out it's independent of the path, and also to calculate this, you just use the antiderivative. It's f of z1 minus f of z2 minus f of z1. It's a pretty neat theorem. It tells you exactly when the integral over a closed curve is 0. It's precisely if it has an antiderivative. So in particular, if that integral is not 0, it means there's some singularity going on. And it's very interesting because usually it's seen as an anomaly, but here singularities are kind of useful. But I'll get back to that later. Okay, and now that we've defined integrals, in the next chapter, if you want, we discover the most important theorem about integration. Actually, there are two of them. One is called the Cauchy-Riemann. I think it's this, Corsi. Saying so again, another easy way of saying, if the line integral is 0, if f is holomorphic, then, again, suppose C is simple closed curve, then the integral over C of f of z dz is 0. And simple closed. And that just means, again, closed means the start is the end. Simple means, I think, no self-intersection. Like, this is not simple closed because it intersects here. So again, as I said, this is nice because if the line integral is not 0, then f has some singularity somewhere. And that's one way, okay? And so it's the first very important result in complex analysis. The second one, in my opinion, is the single most important one. It's called Cauchy's integral formula. Saying that if f is holomorphic, then let's calculate the following integral. 1 over 2 pi I integral over c f of z over z minus z naught dz. Again, it's a singular integral. This integral has a singularity at z naught. So I suppose this is z, and then this thing most of the time blows up at z naught. But it turns out this integral is very nice to evaluate. Its value is just f of z naught. And this is an essential theorem in complex analysis because you'll see it has a lot of consequences. But what's nice is it gives you f in terms of an integral. So maybe if you like, you can think of it as a fundamental theorem of complex analysis. It's very nice, and moreover, the nice thing is you can literally, again, here's what's nice about complex analysis that didn't work in real analysis. You can take this identity and differentiate as many times as you want with respect to z naught. So in particular, if you differentiate this, n times, then you also get the nth derivative of f in terms of z naught is given by an integral, again, f of z over z minus z naught to the n plus 1, up to a factor, so 2 pi I over n factorial. Again, pretty impressive, okay? And so it also gives you the derivatives of f in terms of f. Okay, you might not be impressed, maybe, but using those things, we can prove insane things, okay? So here's some consequences. And this is why I really like this. This formula. So here's some consequences. First of all, and this is very not true for real analysis, if f is once differentiable, then it's infinitely differentiable. Wow. So once you can take one derivative, then you can take as many derivatives as you want. Insane, but it's true. And moreover, here's another nice property. If f is bounded, so if it's less or equal to c in terms of absolute value and differentiable, then it's constant. So in other words, differentiable functions have to blow up at infinity usually. Wow. And also, not only that, you can also use this to prove the fundamental theorem of algebra, which says that any polynomial of degree n has to have at most n roots up to multiplicity. So any polynomial of degree n has n roots. Again, up to multiplicity. Wow. That's impressive. Okay. Okay, n is greater or equal to 1. Okay. So that's one thing. So that was like the integral part of the complex analysis experience. But again, going back to calculus, the next thing you learn are series. So we can have complex series, which are also amazing. Okay, so series. You can define, other things like geometric series. 1 over 1 minus z is 1 plus z squared plus ... And also you can define Taylor series of a function. So on the one hand you have f of z, you have the Taylor series, sum from n from 0 to infinity, fn of z naught over n factorial, z minus z naught to the n. In real analysis, they're not always equal. And in fact, we say a function is analytic if it equals to its power series. Turns out, in complex analysis, again, the beautiful thing is that if you're differentiable, so if you're holomorphic, then you're analytic. In other words, if you're once differentiable, then you automatically equal to your power series. Seriously impressive, in my opinion. And in fact, even if a function is not differentiable, you can still, if it's not differentiable, you can still define a sort of power series, which is called a Laurent series. So I like that name, Laurent. It's one of my favorite names. And Zach, also really cool. Namely, it's like a power series. So an z minus z naught to the n plus terms, but like 1 over that. So 1 over z minus z naught plus, I guess, sum from 1 to infinity of bn z minus z naught to the n. And that works for any function. So again, at least continuous or something. So even if it's not differentiable, it still has this form. And this thing, and again, it's called the Laurent series. Lorenzo. Okay. And this actually is very, very useful, especially in the next section, which are called residues. And that's where the fun really is. That's where you calculate those crazy integrals. But let me motivate this. Laurent series and let C be a simple closed curve. So C is closed. Curve. Again, like this, as simple closed. And take this Laurent series and integrate it over C. Then you get f of z, C equals to sum from n from 0 to infinity, an integral of z minus z naught to the n over C plus, let's just separate this because you'll see in a second why we do that. 1 over z minus z naught over C plus sum from 2 to infinity of bn integral of 1 over z minus z naught over C, and then all dz. Okay, why did I do this? Remember that theorem, the following are equivalent, never gonna give you up, okay? If a function has an antiderivative, then automatically, over any simple closed curve, the integral is 0. In particular, this function here, well, it has an antiderivative, z minus z naught to the n plus 1 over n plus 1. So in particular, this disappears. This disappears, again, by the same argument. That should have been an n. Okay. The only issue is here, and because it has to do with this log, well, technically, an antiderivative is log of z minus z naught. But remember what I told you, log is one of those controversial, functions. So in particular, here, doesn't necessarily have an antiderivative, but that's good because in general this is not 0. So really the contribution of the non-zero-ness comes from this term. And in particular, though, we can evaluate this, I forgot to say. Because sure, the integral is not necessarily 0, but it is equal to something else by this Cauchy integral formula. So remember, we had this thing, f of z over z minus z naught is, I think, 2 pi I f of z naught. Well, this integral is the same thing, except here f is a function 1. So if you calculate this, in fact, you will not get 0, you will get 2 pi I. And so, in the end, after this explosion, what you really get is that the integral of f is 2 pi I times b1. And this b1 is what's called the residue at z naught. Residue at z naught. Simply the junk at z naught. And where z naught is usually the singularity of your function, but that's great because basically once you found the residue, you can actually calculate this integral. And this is why those residues are so important. So let me just conclude. So b1 is the residue at z naught, and that equals to the coefficient of 1 over z minus z naught in the Laurent expansion. In the Laurent series of f at z naught. So, usually then, to calculate those integrals, you will never do this contour thing. You will usually calculate the residue and using the power series of a function, and then it gives you the integral back. And that was a lie. You do use sometimes contours, but it's a nice sort of, nice connection between the world of integrals and the world of power series. And by the way, if you have many singularities, then you just take the sum of a bunch of residues. You just look at where all the singularities are, and you just take the sum. And that gives you your thing. And for many applications, I'm sure you can just check one of many other videos where I calculated integrals using complex analysis. And that's one thing. And lastly, I want to talk about singularities, because using this Laurent series, you can actually classify singularities. There are three types of them. One is called, if you want, the benign singularity or removable singularity. In other words, if a function blows up at a point, how badly does it blow up? And the answer is there are three kinds of badly. One is it doesn't really blow up, and think of this function, z minus z naught squared over z minus z naught. Well, sure, it has a singularity at z naught, but this is just equal to z minus z naught, so it doesn't blow up. That's just a removable singularity, and it means that if you redefine your function at z naught, it actually becomes holomorphic. Then there's something called the pole of order k. Which just means that the Laurent series is actually finite at minus infinity. Think of something like 1 over z minus z naught plus 2 over z minus z naught squared plus, I don't know, plus 3, for example, z minus z naught to the k. So in other words, the Laurent series itself, it terminates, and these functions, they're bad because you have a singularity, but not that bad at all. It still has a pole, and you can actually calculate residues at those poles pretty easily. And lastly, is the bad thing, the malignant case. It's called the essential singularity. Basically, the Laurent series doesn't stop. I know it sounds like a party, yeah, never stop, dancing, but this is a bad thing. Think like e to the 1 over z. That's something equal to the sum from 0 to infinity of 1 over n factorial, 1 over z to the n. The Laurent series just goes on to infinity. And those functions are very bad. Those are the ones you don't really want to deal with. And lastly, using those residues, you can prove other nice theorems. One is called the Boucher's theorem. I like it because it makes me think of L'Oréal. It's like this new product, parce que je le vois bien. Oh, okay. Anyway, so that's called Boucher's theorem, and it's kind of neat. Basically, it says that if G is less than F, then F, you can perturb F by G and still have the same number of zeros. Namely, then F and F plus G have the same number of zeros. Up to multiplicity. So, let me just give you a quick example. For instance, usually f is a very simple function. So take f of z to be z to the 5th. Okay. Then this has 5 zeros, namely 0, up to multiplicity. And basically, in a very small ball, take, for example, g of z is, I don't know, z squared plus 2 or something. The question is then, how many zeros does z to the 5th plus z squared plus 2 have? And again, maybe, I guess in a large ball or something, you find that g is less than f. Again, take a ball of radius 100 or 9,001. So then, the question is, how many zeros does this polynomial have? Well, this is f of z plus g of z. We know that g is less than f, and so f plus G has as many zeros as F. Zeros as F. But we know that F has 5 zeros, so this polynomial also has 5 zeros. It's really cool. It's a very neat theorem, and I think we prove it using residues. And of course, I have just barely scraped the surface. There are other things you can deal with, like argument principle, and then winding numbers, and what was it? Conformal maps. Like you can study maps that preserve angles, and those are, I think, determined by what's called Schwarz-Christoffel symbols. And then there's this whole theory of Fourier transforms, and not only that, so far we just studied functions of one complex variable. There's also functions of several complex variables, which have an even deeper theory. So really, this is like just the start of heaven, and there's more heaven waiting for you. Alright, so if you like this complex analysis overview and you want to see more math, please make sure to subscribe to my channel. Thank you very much.